Assalamu alaikum. Welcome student to this new session. This is our third lecture for the fifth week. We were studying vapor absorption refrigeration system. We did one example in the last lecture. We are going to continue with the second example, which is very similar to the first example, with the exception that now the temperature after the heat exchanger is different than what it was in the last example. So that's the major modification, and there are maybe some little bit of changes. So let's get started with that example numerical. This numerical reads refer to the absorption refrigeration cycles shown in the figure. So this is the figure. So if you look at the figure, the temperatures of the four container are the same. That the evaporator is 10 degree, absorber is 30 degree centigrade, generator is 100 degree, and condenser is 40 degree centigrade. It is the same as we had in last time. The difference is in this temperature after the heat exchanger. That previously we had done it with 52 degrees centigrade. This is 48 degrees centigrade. So that's one of the modification. And there are a little bit of the question is a little bit different than what we had before. So we have to see how to answer those questions. Okay. Find the mass flow rate of the refrigerant and the mass flow rate of the solution returning from the generator to the absorber. So we need to figure out the mass flow rates here. Calculate the heat transfer rates at each of the components. So Q A, Q G, QC, and QE we need to find out. Calculate the heat transfer. Those heat transfer we need to calculate. What is the solution temperature at 0.4? 0.4's temperature we need to find out. So that finally, once we have determined what is the enthalpy of 0.4, we can use that enthalpy information and the solution concentration information to find out what is the temperature at 0.4. As we had done in the previous example, we do the energy balance of the heat exchanger, and then we can find out. This will be a slightly different methods. Otherwise, if you look into carefully, then you will see that it is the same thing. Determine the COP of the system. Find out the COP of the system. Okay. So moving on. First thing is that we want to use our PXT diagram and draw the line, the temperature and the pressure line for the absorber and the generator, and then with the help of that find out what is the because we know the solution temperature also, so we will know what is the concentration. So I have drawn that figure here. If you see, this is the absorber. So absorber is at 30 degree. This is the evaporator at 10 degrees centigrade and condenser at 40 degrees centigrade. So the brown line and the red line. Okay, the corresponding vapor pressure of water is 1.23 and 7.38. So these are the pressure which is in the absorber and in the generator, 1.23, 1.738. So, and the solution temperature in the generator is 100 degrees centigrade. So blue line is the solution temperature, as it reads here, solution temperature. Okay, so 100 degrees solution temperature it is given, so we followed the 100 degree solution temperature line, and it is crossing your condenser line at this point here. From there we look vertically downward, and we see that the concentration value along the x-axis is 66.4. So this is the concentration in the generator, and in the absorber the temperature, solution temperature was 30 degrees centigrade. So this green line is showing this 30 degrees centigrade, which is crossing your gray line or the brown line of the evaporator at this point here, or of the pressure line of the absorber at this point here. So wherever they cross it, that's the state of the solution. So we look vertically downward, so we can read that this concentration is 50%. So solution concentration in the generator is 66.4%, and solution concentration in the absorber is 50%. So with the help of that, we can use the next diagram, the HXT diagram, and we can find out what is the enthalpy value. in those things. So here you go, here it says generator solution temperature 100 degrees centigrade, T saturation of pure water is 40 degrees centigrade. So with the help of that we can determine what is the saturation pressure. So X3 will be 66.4%. X3 here, what is coming out of the generator, is 66.4%. Absorber solution temperature is 30 degrees centigrade, T saturation of pure water is 10 degrees centigrade, so that will give you the corresponding vapor pressure. So X1 is 50%. So X1 here is what is coming out of the absorber. X3 what is coming out of the generator. X1 what is coming out of the absorber is 50%. Mass balance on the generator is carried out for the solution lithium bromide plus water and lithium bromide only. So we are doing mass balance for the solution and for the salt only. So mass balance of the solution leaving the absorber is m dot 3, is that right? And the solution leaving the not absorber, leaving the generator is m dot 3 and m dot 5, and what is coming into the generator is m dot 2. So because a steady flow, a steady state system, so m dot 2 should be equal to m dot 3 and m dot 5. M dot 2 is coming into the generator, m dot 3 and m dot 5 are leaving from the generator, so sum of these two should be equal to this one. So that is what it's written here. So the m dot 2 and m dot 1 are same, 0.6 kilogram per second. It was given. It is not mentioned here, but it is mentioned on the diagram right here that the mass of solution, the mass flow rate of solution from the generator, from the absorber, here, right here it is given, okay, from the absorber is 0.6 kilogram. So this is m dot 1. So similarly it should be m dot 2 because this is the same pipeline, okay. And the salt, lithium bromide salt mass balance will be m dot 1. X1 is the mass of the salt which is leaving the absorber, and m dot 3 X3 is the mass of the salt which is coming out from the solution into the absorber. So what is leaving and what is coming out should be same. So from here, because we know already X1 and X3 and we know m dot 1, so we can figure out what is m dot 3. So m dot 3 is 0.452 kilogram per second. And from this equation again, this equation here on the top, because we have already figured out what is m dot 2 and m dot 3 is, so we can find out what is m dot 5 is. So m dot 5 is 0.0148 kilogram per second. So this is about the same that we had last time. It's not changed much, okay. Obtain enthalpies using the HXT diagram. So with the help of solution temperatures and the concentration value X3 and X1, we can find out what is the temperature, what is the enthalpy values. So I have marked those on the HXT diagram right here. So this was the solution in the generator. So this solution line, solution temperature line, and this is the concentration line. The green one is the concentration line. So wherever they cross, that is the state of state of the enthalpy, or that is the state of the solution in generator. So that value is, this time we read it as minus 54 kilojoule per kilogram, H3 value, okay, minus 54 kilojoule per kilogram. And in the absorber the percentage was 50% and the solution temperature is 30 degree. So the point is crossing here. So from here I can show this green line. This green line is reading enthalpy value as H1 is equal to minus 168 kilojoule per kilogram, okay. So and then the H2 value, because H2 value is after the heat exchanger and the temperature there is known, the temperature of the solution after it is coming out of the heat exchanger, going in from the absorber and coming out of the heat exchanger from this side, from the absorber side, it is given as 48 degrees centigrade. So solution at the exit of the at the exit of the heat exchanger is 48 degrees centigrade. So I draw this blue line representing 48 degrees centigrade, less than 50 and more than 40, so in between there. Okay, and then the concentration will still be the same, because it is the solution which is leaving from the absorber, and the absorber has 50% solution, so the 50% solution is there. So from here I can read H2 value as minus 128 kilojoule per kilogram. So now we know H1, H2 and H3 enthalpies of this solution at three different points. So this is X1, X2, X3. X1 0.5%, T1 of 30 degree, H1 is minus 168, X2 and X1 are same, 0.5 or 50%, T2 is 48 degree, so H2 is minus 128, because we found out what is X1 is. What is X1 is right here, and what is X3 is. X2 we did not find it, but we don't need to, because X1 and X2 are same. It is the same solution which is leaving the absorber and going into the heat exchanger. So what is coming out of the heat exchanger must have the same concentration. That's why X2 is equal to X1. Okay, so minus 128. Then X3 is 66.4%, and T3 is 100 degrees centigrade for solution temperature in the generator. The corresponding value from the HXT diagram is minus 54 kilojoule per kilogram. Enthalpy at state 4 is found from an energy balance on the heat exchanger. So enthalpy at point 4, it is the point which is after the heat exchanger here. Okay, so we want to find out enthalpy of this point. So the energy balance about the heat exchanger, that's what we're applying. Whatever energy lost by the hot fluid coming in into the absorber from the generator is the same amount which is absorbed by the solution which is leaving the absorber and going into the generator. So from that principle, okay, here you go. M dot 1 into H2 minus H1 is the heat gained by the solution which is coming out from the absorber going into the heat exchanger, and M dot 3 H3 minus H4 is the heat lost by the solution, generator solution, which is coming out from the generator and going into the heat exchanger. So these two must be same. So if we equate it, we know all the other values except H4. So H4 calculated to be minus 107.14. So we found out all the enthalpies except the enthalpy of condenser and evaporator, which is pure water. So for that we can use the table. So from the property table of water, table A1, and I think I copied it here, right here. Okay, so those values are already highlighted. Okay, H5 is Hg at 100 degrees centigrade, so that is 2676, and H6 is saturated liquid at 40 degrees centigrade, 167.45. H6, now if you look up in the diagram, is right here. So after the condenser we get a saturated liquid at 40 degrees centigrade, so that value is 167.45. 40 degrees centigrade saturated liquid, 167.45 right here. Okay, similarly H7 is Hg at 10 degrees centigrade, so that is 2519.19 from the table. At 10 degrees centigrade saturated vapor, so 10 degrees centigrade saturated vapor is 2519.9 kilojoule per kilogram. Okay, so those are the values from the A1 table, A1 steam table, okay, or table for water. Okay, now the heat transfer rates can now be determined using energy balance for each of the components. So it's same thing, we are doing the energy balance of the generator. So this is another style of writing. So it's same energy balance that we had seen before. M dot 2 H2 is the heat transfer into the generator due to the solution coming in from the, you can say, heat exchanger or from the absorber, and plus Q dot G is the heat which is supplied into the generator. So this is what heat which is flowing or energy flowing into the generator is equal to M dot 3 H3 plus m dot 5 H5. So these are the mass flow rate which is leaving the generator. So m dot 3 is coming towards the heat exchanger, or it is going into the absorber, and m dot 5 is the one which went to the condenser. So energy flowing in should be equal to energy flowing out. So if we solve this equation, because we know all these mass flow rates and the enthalpies we found out, so Q dot G is 448.44 kilowatt. Similarly, energy balance around the condenser, so in case of condenser, heat expelled is this much, and plus m dot 5 and m dot 6 is also leaving, only m dot 5 H5 is coming in. So Q dot H plus m dot H6 is equal to m dot 5 H5, and when you solve the equation you will get Q dot H is equal to m dot 5 into H5 minus H6. Okay, so if you solve this equation, you will get 371.26 kilowatt heat rejected in the condenser. Then in the evaporator, the heat absorbed will be Q dot L is equal to m dot 5 into H7 minus H6 through the energy balance equation. We get this one. So this is the cooling load, or this is the refrigeration produced, is 348.16 kilowatt. Similarly, absorber, the energy balance equation. So Q dot A is the amount of energy which is leaving the absorber, and m dot 1 H1 is the mass flow rate which is leaving the absorber. So energy out because of the mass flow out is m dot 1 H1 plus Q dot A is equal to m dot 4 H4, which is coming from the generator, and m dot 7 H7, which is coming from the evaporator. So these two are flowing in and these two are leaving. They should be equal. So we know from our mass balance that m dot 4 is equal to m dot 3, and m dot 7 is equal to m dot 5. M dot 4 and m dot 3 are same. It has to be, because this is 3 and this is 4, so the same mass is flowing from the pipe. So m dot 3 m dot 4 should be same, and whatever is leaving the generator has to pass through 5, 6 and the evaporator, and 7. So m dot 5 and m dot 6 and m dot 7, they are all same. So that is what written here, that m dot 7 m dot 5 should be same. So replacing all the values, we get Q absorber as 425.3. Okay, now from the HXT diagram, now we want to find out what is the temperature at point 4, that is the point after the generator, after the heater, for the solution coming out of the generator, this point here. We want to find out what is the temperature here. We can find that out quite easily, because we know what is the enthalpy at point 4. So once we know the enthalpy, we know the solution temperature, we can use those two information, solution and solution temperature and enthalpy information, to find out what is the temperature at point 4. No, not solution temperature, sorry, no, that's wrong. We know the concentration, because the concentration will be same as in the generator, and the enthalpy. So concentration and enthalpy we know. We need to find out what is the solution temperature here. It started with 100 degrees centigrade. At point 3 we could have taken 100 degrees centigrade, but not at point 4, because as it passes through the heat exchanger, it has lost some heat to the other fluid. So let's figure that out. So here is that line. So we are getting the concentration at point 4 was 66.4% right here, and we know the enthalpy value is 107.10, as we have calculated by energy balance. So the point is where your enthalpy 107, this dashed line is the 107 enthalpy, minus 107.10 enthalpy. Okay, the dashed line here, the brown dashed line, is the enthalpy line that we have drawn, and here it is the concentration line. The green line is the concentration line. The solution line must pass through this line, so you have to draw a parallel line between 70 degrees centigrade solution temperature and 60 degrees centigrade solution temperature. So by looking at the 107 value here, you try as close as possible to draw this line. We should pass from this point which is crossing this green line and the brown line. So that temperature, if you look it up, it will be 69 degree. It is very close to 70 degree temperature. So that's the temperature value we have taken. Let's go see it. So T4 is 69 degree. That's how this 69 degree temperature has been figured out. Okay, now COP is Q dot L upon QG. So that is equal to 0.776. Once you do the QL value right here, from here, and QG from there. So 348.16 divided by 448.44. So you get a COP value of 0.776. So it is higher as compared to for a vapor absorption system without an heat exchanger. So this is all about the vapor absorption cycle. Now we want to look it up and we want to do a comparison of the vapor absorption refrigeration system compared to vapor compression refrigeration system. So a comparison between the two. So a liquid is compressed instead of a vapor. We are compressing, we are pumping out a solution. So we are compressing a liquid. Thus the work input is very small, 1% of the heat supplied to the generator. So that's why normally we ignore in our calculation of COP. So the required energy, we consider only the generator, and the pump is ignored because it is 1% of the heat supplied to the generator. Can be used to furnish heating and cooling simultaneously. Much more expensive. This because the bulky system is a larger system, so it is expensive system, more complex and occupy more space, much less efficient. COP R of this system is less than 1, as you have been seeing it. Whatever calculation we did, it always comes out to be less than 1, requiring much larger cooling tower. So sensible heat is required. So mass flow rate has to be very, very high. More difficult to service since they are less common. Should be considered only when the unit cost of the thermal energy is low and is projected to remain low relative to electricity. So this is only viable where you have waste heat energy available, either waste heat coming from a steam turbine or from a gas turbine, or if you have a solar system installed in your factory, then it is a viable thing. Or sometimes some industries are using steam, so waste steam is available, then you can use this system. So a cheap source of heat has to be available for a longer period of time to cover the cost, the investment cost. To cover the investment cost, you want to have that cheap source of heat available for at least 10 years and 15 years. Okay, then it will be useful. Primarily used in large commercial and industrial installation. Now the application of refrigeration. So as you know, refrigeration is used in almost all parts of our life. But here is a brief of the application of refrigeration where we have been using it. So in water cooler, that's one of the, in hot weather like the weather these days, everybody wants cold drinks. So in water coolers, storage type in which the evaporator coil is soldered on the walls of the storage tank. Instantaneous type in which the cooling water and the evaporator coils are entwined and soldered together. So we have one such system installed in our NED University. In mechanical also, or if you look it up in the automotive department also, we have a cold water cooler where the refrigerant is actually the evaporator is a coil, and it is dipped inside the tank of the water. So directly we get chilled water at 7 degree or 10 degrees centigrade there. Ice making plant, a complete installation including the ice maker itself together with the associated refrigeration machinery, harvesting and storage of equipment, and the building, classified by the type of ice they produce as listed below. So we normally we are familiar with only one type of ice, the block ice, okay, but there are other types of ice. They call it a edible ice, which are small flakes or small chocolate type of tube that you use in your drink, okay. Block ice, this is the famous one that we normally use in our country. Tapered rectangular metal cans filled with water are immersed in a tank containing refrigerated sodium chloride brine maintained at -10 degree to -11 degree centigrade. So the refrigerant is the evaporator is basically dipped inside a tank, and the tank is filled with the brine solution, that is water containing sodium chloride into it. 70% water, 30% brine, 30% sodium salt dissolved into it. So that one can go as low as, it goes as low as it can go as low as -30 degrees centigrade, -40 degrees centigrade it can go, but we need to maintain it at -10 degree because we just want to make ice which will start making at 0 degree centigrade. Flake ice, this is what we call it, edible ice, okay. A sheet of ice 2 to 3 millimeter thick is formed by spraying water on the surface of a refrigerated drum and scraping it off to form dry subcooled flakes, usually 100 to 1000 millimeter square in area. In some models, the drum rotates against a stationary scraper on its outer surface. In others, the scraper rotates and removes the ice from the inner wall of a double-walled stationary drum. The drum is mostly mounted vertically. Typically, refrigerant temperature in a flake ice is ice machine is -20 degree to -25 degree. So this is another type of ice. As I said, it could be in a flake, or it could be just like a small cylindrical shape type of ice, which is used in the drinks or used in other applications. Sometimes freezing the product also, which are open in this space. So you just spray it on your fish, or on your fish mostly. That's what I have seen, that they sprayed it, or on chicken also. If you have chicken, large tray of the chicken meat, then you spray this flake kind of ice on top of it, so it doesn't spoil easily, okay. Tube ice. Water is frozen on the inner surface of a vertical refrigerated tubes to form hollow cylinders of ice about 50 millimeter in diameter with walls 10 to 12 millimeter. The ice cylinders are released by defrosting the tubes and are chopped into pieces about 50 millimeter long by a rotating cutter as they slide out. So this is the one. This is the more common one, which is used as a or which is called as edible ice. So plate ice. Water is frozen on one face of a vertical refrigerated plate, and the sheet of ice is released by running warm water on the other face of the plate. Ice plants typically use ammonia as the refrigerant due to its high refrigerating effect per kilogram of the refrigerant and low specific volume of vapor. So milk and milk products. Fresh milk must be cooled within 2 hours to 4 degrees centigrade or lower. So otherwise the milk will become spoiled. So within 2 hours you have to reduce its temperature to 4 degrees centigrade under hygienic conditions to prevent a rapid growth of microorganisms present in the milk. Whole milk for human consumption is pasteurized at 75 degrees centigrade for a short time and then recooled to 4 degrees centigrade immediately. Milk for other products is treated. For ice cream, for making ice cream, comprises fats, not always dairy, milk protein, sugar, and additives such as emulsifiers, stabilizers, colorings, together with extra items such as fruits, nuts, pieces of chocolate, etc. So those are combined in the milk. Okay. The most useful refrigerant for ice cream continuous freezers is ammonia, which will be at an evaporating temperature of minus 35 degrees centigrade to minus 30 degrees centigrade. The freezing process covers a wide band of temperatures starting just below 0 degrees centigrade and not finishing until minus 18 degrees centigrade or lower. The manufacturing process is in three main stages: mixing, freezing to a plastic state, and hardening. So that's how this ice cream is made. First mixing, then freezing to a plastic state, and then at the end hardening it so that it doesn't melt away. Food refrigeration and freezing. So application of refrigeration in food refrigeration and freezing. Foods which are not to be frozen are stored at a temperature just above their freezing point, providing this does not damage. Exceptions are fruits such as bananas and lemons. Produce which is to be frozen must be taken down to a temperature low enough to significantly reduce the amount of free moisture and hence bacterial activity. So there is a special technique. You cannot just freeze vegetables or fruits and then think that they will not be boiled. They may get what is called frostbite or something like that. So it has to be at a certain temperature. Depending on the product that you are trying to freeze, you have to use a certain temperature for it. Okay. A distinction must be drawn between the cooling process and the subsequent storage. Careful control of temperature and humidity is needed when cooling warm produce, since evaporative cooling plays a part in both product temperature and wet loss. Quick freezing. In air blast freezing, the air temperature is of the order of minus 40 degrees centigrade and the air speed over the product is high. Indirect contact freezing, in which product in rectangular packages such as ice cream in flat cartons are pressed between the horizontal flat refrigerated plates. The vertical plate freezer is used for loose products such as wet fish. Immersion freezing, that is material to be frozen in fully immersed in a cold liquid such as a brine. So these are the different application of refrigeration in our daily life. So I'm going to append a couple of videos at the end here, and I hope you will understand and it will create some kind of interest in you as far as the application of refrigerator or refrigeration is concerned. So I thank you very much once again, and if you have any questions, then note it down, then we will discuss it during our live session. Thank you.